Welcome back everyone. Welcome to those of you seeing this online as well. Today we're going to talk about a new kind of differentiation called implicit differentiation. Now before we start on this, I want to point out that this is the topic where that notation I was telling you guys about, Leibnizian notation, differential notation, is going to be very useful. Not only useful, but probably practically necessary for doing these problems. So just as a recap of what Leibnizian notation is, instead of writing a derivative as f prime or y prime, you can write it in a fractional way, so to speak, as dy over dx, yes? So you can express a function like that. You can express the derivative operator, not just as a prime, as an apostrophe. We can also just write it as, d dx. So this is a derivative, this is a function, this is an operator acting on a function. But they're both in Leibnizian notation. Does that make sense? And the other thing, do you guys remember the chain rule? Someone remind me what the chain rule is. Let's say if I have dy over dx. If I want to find that in a chain rule fashion, the Leibnizian way of expressing this is as a product of two derivatives. Dy over some variable we create, du, and what goes there?
du over dx.
Yes, du over dx. And we prove that in a very rigorous fashion, but again, just off the cuff, intuitively, you can think of these du's as offsetting each other. Don't think of them as strictly canceling again, because these aren't just simple fractions, these are derivatives, they're functions, and the properties of functions are a bit more complicated than the properties of fractions. But still, as an off the cuff way to remember the chain rule, you just think of the du's as offsetting each other. So, using Leibnizian notation, someone tell me what this equals. What is the derivative? The derivative operator acting on the function, let's say, x cubed.
3x squared.
Yes, 3x squared. Nice, simple power rule. Alright, now let's suppose we have this. We just change the x to a y. And let's suppose we have to make the supposition that y is some function of x. Because if it's not a function of x, then the derivative of this guy is just what?
0.
Yeah. It doesn't depend on x, it's just 0. So y has to be some function of x. So here's the issue. In the previous example, the thing that we were cubing, the variable that we were cubing and this, they matched each other. So we could just simply straight away apply the power rule. But in this case, our variables here and here do not match. So anytime that happens, that's a trigger to use the chain rule. In other words, I can break this guy up. So if you want to put in that notation, the derivative of y cubed with respect to x can be broken up into a product of two derivatives. The derivative of y cubed with respect to some variable we create u times du over dx. Now what's the natural choice for u in this scenario? What am I cubing here?
Y.
Yeah. So for these situations, the natural choice for you is just, let it be y. So the derivative of y cubed with respect to y times the derivative of y with respect to x. How can I simplify that? See, now the variables match. That guy matches that guy, just like I did here.
Oh,
So this whole thing equals what?
3y squared.
Yes. 3y squared times that dy over dx hanging out the side. And we can't do anything more with that, so we just leave it as is. So again, now notice the difference in the final products. Here we didn't have some derivative hanging off the side, but in this case where they don't match, we did. We had that dy over dx. But again, all it is the chain rule with our u being equal to 1. Alright, I want you guys to take a minute to try this one. Again, in Leibnizian notation, in this nice differential notation, find the derivative with respect to x of x times y squared. Or again, y is some function of x. Before you guys start, what rule differential rule am I going to have to apply here?
The multiplication rule.
Yeah, product rule. So, have a go at that for about a minute or two. Alright, so how do y'all feel?
Pretty good.
Pretty good? Now, when you guys are starting off, I want you to do it in this kind of distributive way with the differential operator. So, I gotta use product rule, which is this guy times the derivative of this guy with respect to x, yes? So, x times the derivative of y squared with respect to x plus what?
dx over x times y squared.
Yeah.
Yeah.
The derivative of x, the derivative operator acting on x, taking the derivative with respect to the independent variable x. This piece, of course, equals what? U. What's the derivative of x with respect to x?
This one.
That's just a simple one. But now here, the derivative of y squared with respect to x, now I've got the situation where my variables don't match, just like they did up here. They didn't match. So I need to fall back on using what rule?
The chain rule.
Yeah, get a nice chain rule expression. So, let's use a different color. This guy equals the derivative of y squared with respect to y times what? U.
I don't know.
Alright, Jordan.
dy over dx.
dy over dx, remember. You set up the chain rule in such a way that the variables you create, the differentials of that, offset each other. Right?
Right.
Alright, so in this case, the dy's will offset each other and they'll regenerate what I'm trying to simplify. Does that make sense? Alright, well, what's the derivative of y squared with respect to y?
2y.
Right, they match. And with that, we are done simplifying our derivatives. So the final answer, the final derivative of this product is going to be 2 times y times x plus, oh, I forgot one thing. What did I forget?
dy dx.
Yes, don't forget the dy dx. It's a very easy thing to forget, but you always have to have it in if you have a y. Then plus y squared times 1, which is, of course,
Y squared.
y squared. Precisely. So that is my derivative of x times y squared with respect to x, assuming y is some function of x. Alright, so computational, I guess this is kind of cool, right? The question is, what can we do with this visually? What can we do with this graphically? So, any questions before I get rid of this on the board here? Any questions? No? Good? Alright,
Just to be sure, the dy dx is like absolutely necessary to have in your solution. Like you would probably take points off if somebody didn't have a dy over dx in their
yes,
answers.
it's completely wrong. I mean, the dy over dx is part of the chain rule,
Okay.
right? It's the second part of this chain rule. It's right here, except instead of a u, we got a 1.
Okay.
So yeah, you need the dy over dx, otherwise that indicates that you don't understand that you're using the chain rule here.
Okay.
Alright, so yeah, what can we do with this process computationally? I mean, visually and graphically. Well, as it turns out, with this idea at hand, we can actually find the slopes at a particular point of a graph that it's not a function. That's not a function, so I'll read that again. You can find the slope of a point on a graph that is not a function. That's not something that passes the vertical line test. So someone tell me out here, what's a classic function? Sorry, not classic one. What's a classic graph? A classic shape in the coordinate plane that you can express in one line, but that's not a function.
Like a circle?
Yes, start with a circle. What is the equation of a circle? Say it's centered at the origin.
X squared plus y squared is a squared.
Alright, x squared plus y squared is a squared, and let's keep it simple, let's say it's a circle of radius 1. Like that. Okay, so the reason why this makes sense for the equation of a circle, just a little detour for a second. All this is the Pythagorean Theorem. Okay, you have a triangle, and you're just rotating that triangle. But whatever you have as your x and your y, in order for it to be a circle, when you add the squares, they have to equal 1. Make sense?
Yeah.
This is just the Pythagorean theorem, and the Pythagorean theorem creates this nice circle. Okay, good. All right. So, what if I want to find the slope, the instantaneous slope, the slope of the tangent line to the point, let's say 1/2. And in order for this to be a unit circle of radius 1, what does this y-coordinate have to be? So you should probably know this from trig.
Square root of 3 over 2.
Yes, square root of 3 over 2. We want the sum of the squares to equal 1. So there we go. All right. What I'm going to show you now, I'm just going to show you how to do this. Okay. In about 5 minutes or so, I'm going to show you the why behind, the process here. But for now, I'm just going to show you what the process is. Okay. First thing is you let y. Let's say y is some indeterminate function of x. We don't know what function of x it is, but let's say it is some function of x out there. Well, with that in place, and let's say this always equals 1, because this is always true on a particular neighborhood, let's say, I can take the derivative of both sides. Again, I'll explain in more detail why you can do that, but for now, let's just look at the process. So, you start with your equation, falling apart here. You take the derivative with respect to x of both sides, the d dx of the left equals d dx of the right. And now someone tell me how I can simplify this. Start with the easy side. What does that equal? What's the derivative of 1? Nice. Yeah, nice horizontal line, no slope. Constant. Derivative of constant is always 0. Alright. Now this, again, here's where your differential notation becomes valuable. When I have a differential operator, I can think of it in a distributive way. For example, if you have an addition sign or a minus sign, I can distribute this operator to each of the terms inside. So we prove that using our derivative rules. We can do that.
Yeah.
This is the derivative of x squared with respect to x. And this is the derivative of y squared with respect to x. What's that guy right there?
2x.
2x. And now, this is exactly the problem we did a minute ago, or part of the problem we did a minute ago. What's the derivative of y squared with respect to x? We gotta use the chain rule, but we found out that it was equal to
2y times dy over dx.
yes, again, by way of the chain rule. All we're doing really is the chain rule, just with our use being y. So, I have 2x plus 2y dy over dx, where dy over dx is geometrically the what? Geometrically, it's what quantity?
The slope.
The slope, which I'm trying to find, and that equals 0 for any x and y.
Okay.
And any slope at that point, x and y. So, what am I going to do next? If I want to find the slope at this point? Someone help me out here.
Subtract 2x from both sides.
Yeah. Subtract 2x from both sides. And basically just solve for dy over dx. Solve for your general slope. dy over dx, negative 2x over positive 2y, which comes out to be
Negative x over y.
negative x over y. In other words, for any point on this circle, if you know the x-coordinate and you know the y-coordinate, the instantaneous slope at that point in the circle is just those two coordinates divided by each other through a negative sign in front of it.
I thought it would be y over x because slope is defined as y over y.
This is the slope of the tangent line. So, the instantaneous slope, I'm really referring to the slope of the tangent line at this point. So that was a good observation. 1/2 root 3 over 2. The slope of the tangent line is the slope of this fellow right here. Yes?
Yeah.
Mm-hmm.
The slope of this fellow right here is not y over x, rather negative x over y. So all we gotta do for this is negative one half all over root 3 over 2, which simplifies to what?
Negative root 3 over 3.
Yeah. 1 over root 3, which is negative root 3 over 3.
And we can simplify that.
Oh, this is simple. This is the simplified form. All right. Now for this particular shape, I actually could have done this problem without any calculus, just knowing some facts from geometry. Does anyone see how?
That line is perpendicular to the other line.
Exactly. Anytime you have a line tangent to a circle, that's going to be perpendicular to a line that contains the radius, so to speak. Right? Always has to be true for any circle. Line of tangency, line containing the radius, always perpendicular. And I can find the slope of this line containing the radius just by doing what? This is what you were talking about a second ago. The slope of this little line segment is what in terms of these coordinates?
Y over x.
Right. So let's say here the dotted line, dotted slope, y over x, in this case,
Square root of 3. Yeah, just square root of 3.
yeah, just square root of 3. Square root of 3 over 2, all divided by 1/2. The 2's go away, and we're left with root 3 for the slope of this dotted line. The slope of the line perpendicular to it is that. And we could find this just using some geometries by noting that if you have two lines that have slopes m1 and m2,
Should equal to -1.
yeah. If this is true, if the product of your two lines, the slopes of those two lines, is -1, then line 1 and line 2 are perpendicular.
So that slope times that slope is not -1.
It is.
Yeah. So we set this up like root 3 times negative root 3 over root 3 is negative 3 over 3, or 1. So the way we could have proceeded here is by using this fact and said, okay, without any calculus, I have root 3 times the slope I'm looking for. Let's say this m2 is the slope of the line of tangency. If that needs to be -1, then just using some algebra, m2 is that fellow there, which, as Jordan simplified earlier, was negative root 3 over 3. So in the case of this nice shape, this circle, there are two ways to tackle the cat, so to speak. So any questions about that? So in general, though, this is an equation you want to know, because sometimes you're not going to have nice shapes like a circle, so something weird. But it'll still ask you, hey, find the perpendicular line, find the slope of the perpendicular line at this point. And for that, you'll have to utilize this fact. Well, really, I should have boxed the entire statement, which is this. If two lines, L1 and L2, are perpendicular, then the product of their slopes is -1. So, sometimes, let's see here. Another word for perpendicular starts with an N. Does anyone know what it is?
N?
It starts with the letter N. It comes up a lot in physics and engineering.
What was the question?
What's another word for perpendicular? A synonym for perpendicular that comes up a lot in physics.
Normal?
Yeah, like something's resting on an incline. The surface exerts what's called a normal force. Perpendicular force perpendicular to the surface. So find the slope of the normal line just means find the slope of the perpendicular line. And, normal line at that point. And we just found out that was root 3. Does that make sense?
Yeah. So we're gonna have to know our basic geometry formulas, such as m1 times m2 is -1 for this course.
Yes, you will need to know this, because you'll get questions. For example, if I want you to find the slope of the line perpendicular, say to this point, and it's not a nice circle, then I can't start off with finding the slope of the perpendicular line. Like
Right.
this. I can only do this because the circle is a very nice shape. But if you have something weird, then this is not the starting point of the process is the ending point.
Okay.
First step is to use calculus to find M1, and then use geometry to find M2.
Okay.
All right. We all good? All right. Now, what if, let's ask some further questions here, follow-up questions. So someone tell me, and this is another powerful application for implicit differentiation. We can ask questions like this. Find the places on the graph, find the points where there's a vertical tangent line. So visually we can tackle that like this. I mean, we have a nice picture for a circle, so where do the vertical tangent lines happen?
The x-intercepts.
Yes. Let's tidy up this picture a little bit. So, and like Jordan said, we got vertical tangent lines at the x-intercepts. So, draw one like so. And I got another vertical tangent there and there. Yes?
Yeah.
What if I also want to find horizontal tangents? Where would that be visually?
The y-intercept.
Yeah, y-intercepts. There. And we got another one right there. And that's using the picture, right?
Yeah.
Do you agree? Okay. Now, what if we didn't have the picture to guide us? What if we just had the equation? So someone remind me, what was the derivative for a circle? Or this circle in particular?
Negative x over y.
Negative x over y. When does this thing have a slope of 0?
When x is 0.
When x is 0. So, take x equals 0. You stick it in your equation. X squared plus y squared is 1. If x equals 0, then 0 plus y squared is 1, and then y equals what?
1.
1 and?
Negative 1.
Yeah, plus 1 and negative 1. That's these two horizontal lines right there.
Good.
Yes? Now, similar argument. If I wanted to find the places where I have a vertical tangent, what do I look for here? I look for the values that make what 0?
Y 0.
Right, make the denominator 0. That happens when, let's see, it's the same deal. Instead of substituting 0 in for x, I substitute in for y. So I have x squared plus 0 squared is 1. X squared is 1, and so you have x being plus or minus 1. These are these two vertical lines right here. And notice they're not asymptotes because I actually have points defined there and there. Make sense?
Yeah.
Go ahead.
All right, cool. So that's our vertical tangents. We also did horizontal tangents. Let's see here. What if a question asks you to find the second derivative, which is expressed in Leibnizian notation like this.
In what type of notation?
Leibnizian notation. So Leibnizian notation is just differential notation.
Okay.
It's with these lowercase d's
Okay.
running around everywhere. So in Leibnizian notation, this is the expression for the second derivative.
Right.
So actually, let's have a quick little recap about higher order derivatives, the notation anyway. So when we talk about higher order derivatives, in the last video, we only used it in terms of like f prime, f double prime. F to, let's say, put one more in there. F to the third, and we could all go all the way up to f to the nth. Well, the nth derivative, right? And let's throw a x in there just to be a little more complete. Now, in differential notation, if I say, y is equal to f of x, what's another way I can write f prime?
dy over dx.
Yes, dy over dx. An incrementally small change in y over an incrementally small change in x. Now, I can take this and break it up into operator notation, which is d dx of y, yes?
Right.
So, the second derivative, this guy, is just going to be d dx of the first derivative, yes?
Okay.
dx of dy over dx. And so where this notation comes from is you can just roughly think of it as, d times d. So that's where that d with a random looking 2 comes in. D squared y. And the bottom is dx. We got a dx times a dx, so to speak. So that's a dx squared. It's not really multiplication that's going on here, but it's just how they write it to make the notation more easy to memorize, to make it more consistent. So that's the second derivative. In Leibnizian notation, it's the third derivative.
It's supposed to be a 3 on that x, right?
Oh yes, good catch. 3 on that x. And going all the way down, the nth derivative is written like so. Cool?
Yeah.
Good.
And it all follows from operator notation and distributed across.
Yeah.
So, if I want to find this guy, then again, just using what I got there, this by definition is ddx of dy over dx. Yes? But what was dy over dx?
Negative x over y.
Right. So I can just substitute now negative x over y and then do what rule? Not the multiplication rule, not the product rule, but
The quotient rule?
yes. So someone remind me, what is the quotient rule?
Low times derivative of the high minus high times derivative of the low all over low squared.
Yes. Or more simply, low d high minus high d low over low squared. As I told you guys last time, a good way to remember this is just as the Adam Sandler rule. Because if you say this at an Adam Sandler accent, it just really sticks.
Huh.
Have you heard of this before?
No.
Should I do it for
have
you?
no
You
idea.
know who Adam Sandler is?
Yeah.
Happy Gilmore,
Yeah. I know.
Big Daddy, or something like that.
Yeah.
Yeah. So, low d high minus high low all over low squared. Yeah, not my best version, but it'll do. So, low times the derivative of the high, d dx of the high minus high, get more space here, times the derivative of the low, so d dx of y, which is just dy over dx, all over y squared. All right. I'm going to
And-
simplify the numerator, yes, Jordan?
Just a quick question.
Sure,
D
sure.
over dx would be in the numerator, right? That would be in the high, right? Like d over dx or...
Yeah, it's low times the derivative of the high.
Okay.
And I'm taking the derivative with respect to x. That's why I carry this
Okay.
d dx with respect to x notation.
Okay.
So, minus high d low over low squared. I'm looking good to go.
Okay.
So, how can I simplify the numerator in some way? What's that piece right there?
-1.
Minus 1. And of course, the derivative operator in x acting on y is just another way of saying
dy dx.
dy over dx, yes. So I have y times -1, negative y, minus minus becomes plus, and then I got that dy over dx, and that's all over y squared. Am I done with this problem?
No.
No, I want my final answer, just like for dy over dx, to be only in terms of x and y. So remember, dy over dx was negative x over y. I just things in terms of x and y. I want the same thing to hold true right here. So any ideas how I can get something just with x's and y's?
You can substitute negative x over y for dy dx.
Absolutely. This thing right here, we determine was negative x over y. That was part one. And with that substitution, we are done. It's negative y plus x times negative x over y, or minus x squared over y. And that entire thing's over y squared. Think about it. If the problem doesn't ask you to simplify, just leave it like that. It's totally fine.
But you can still simplify
You
it.
can if you want. But on quizzes and tests and things, you want to be efficient. So if the problem doesn't ask you to simplify, just leave it and move on.
That shows that you get the point.
Yeah, shows that you get the point, precisely. And that's really all we care about. So these are the second derivatives, higher order derivatives for more messy functions. They're kind of cool in that you not only substitute the first derivative here in the operator, but then you're going to have a place further on in the work where you do the substitution again. Does that make sense?
Mm-hmm.
And yeah, like the third derivative would have to include a similar sort of process where you substitute not only maybe the first derivative, but the second derivative as well. Yeah, that's how you tackle higher order derivatives.
Nice.
Any questions about this? All right, cool. So that's the entirety of the how behind this process, okay? Now some of you may be asking, okay, that's how you do it, but why are you allowed to do what we did?
What is that?
Why are we allowed, for example, to assume that y was some definite function of x? Even if we didn't know what it was, we just assumed it was some function of x, yes? And then we also said, okay, with that in place, we can just take the derivative of both sides. So we made two assumptions, on the surface anyway, that y is a function of x, and also that we can just take the derivative of both sides, and that preserves equality somehow. But that's not necessarily true. So let's see. Let's draw the circle again without all the lines. And again, it's a unit circle, so let's say x squared plus y squared is 1. Yes? You may think, how can I say y is just one definite function of x? Because when you solve for this, what happens? If you solve for this in terms of y, you get y squared equals
1 minus x squared.
1 minus x squared, but then you get y equals what?
The square root of 1 minus x squared.
Yeah, you get that, but you also get what else?
1 plus x and 1 minus x.
Yeah, plus or minus, plus and minus. Like a circle is these two semicircles conjoined together, yes?
Right.
So how can I just simply assume, like I did before, that y was just one definite function of x? Clearly in this case, it's 2, right?
Mm-hmm.
And this also applies, like, let's say we have a more complicated shape. So this guy here is what's called the folium of Descartes. It's a nice little petal type thing. Goes like this and goes like that. That is going to be a -2. It's also a -2. And that provides with the vertical asymptote, sorry, the slant asymptote for this guy. And make that a little more accurate, it's an asymptote.
What is that?
This is what's called the folium of Descartes. This is what it is visually. Looks like this. That's 3. That's 3. That's this little peak there, so to speak. And just like a circle, it has an equation. A lot of x's and y's on one side. X cubed plus y cubed minus 6x1 equals 0. This is called the folium of Descartes. You can tell it's algebraically a much messier expression than a circle. And we got infinitely many of these kind of shapes that are much messier than that. So folium of Descartes. How do I spell Descartes?
T-E-S?
Yes, folium of Descartes. Good. So if I were to do implicit differentiation on this guy, it doesn't look like I have a chance to express y as a function of x. Not only can I in this case I had two functions of x, so that also raised the question, why can't I just assume it's one? In this situation, it just looks absolutely hopeless to even solve for y as one definite function of x. Yes?
Yeah.
Okay. And then even if we could find y as a definite function of x, why are we just simply allowed to take the derivative of both sides of an equation and pretend that that preserves equality? For example, just think of an algebra equation, from algebra 1 algebra 2. If you did this on a test, let's say x squared equals 25. You're like, hey, that's an equality. I can just take the derivative of both sides, right? And get 2x equals 0. Oh, so x equals 0. That doesn't make sense, does it?
No.
No. In general, a derivative is not an equality preserving operator. So I'll say that again. A derivative operator, in general, does not preserve equality. It only preserves equality if your right sides and left sides actually happen to have the same graph on a particular neighborhood, a particular region of two-dimensional space. Okay? So we have two things we want to address. Why can we just assume that y is some definite function of x? And secondly, even with that in place, why can we just take the derivative of both sides? So what are the theory here? Oops, falling apart again. This board is having an identity crisis. Okay, well, I got a little new here. So, first thing. The key to understanding why we can do what we do is we're going to just take any point. We're going to do things on a point-by-point basis, on a case-by-case basis, okay? So for any shape, and I really shouldn't have erased the full name. Oh well, I can draw it again. Start with a circle. Let's pick any point. Say we pick that point. You can pick any point you want, but let's say we pick that one. If I take some neighborhood of that point and blow it up, so we zoom in, I can find, because it's a nice smooth curve, I can find some function y of x. And maybe it goes off and does some other thing afterwards, but I can find some function y of x that exactly matches this graph in some neighborhood of this point. So again, the particular point, don't confuse y with y of x. The particular point here is this one x coordinate and one y coordinate. But y of x stands for this guy in green. And what I'm saying is, because this is a nice curve, I can find some function of x, y of x, that exactly matches the graph of the original. So, graph in green matches the graph in black on some neighborhood. Okay, not everywhere, but on some neighborhood. And that's really all I need then to write, oh, at this point, in the context of this point, it's certainly true that, because we're on the unit circle, that x squared plus y of x squared equals 1. Yes? On this neighborhood, that is a true statement. Does that make sense?
Yeah.
Okay. So the next question is, okay, why can't I just take the derivative of both sides? Well, as long as I have the same graph, and not even necessarily everywhere, as long as I have the same graph on some neighborhood, then on that neighborhood, the slopes of the graphs have to be the same. Does that make sense?
Think so. Can you say that again?
Right. So think about it this way. Y of x on this interval, so I chose a very nice shape, a circle. We can actually solve for y of x explicitly. When I'm right here, y of x happens to be the positive square root of 1 minus what?
X squared.
Yeah, 1 minus x squared. So if I take this guy, 1 minus x squared, and I square him, so we're only thinking in terms of this neighborhood, but if I square him, and to him I add x squared, That's going to always equal what? On this interval anyway. This neighborhood, sorry.
That's just gonna be 1, right?
1. Which is, this line right here.
Oh, okay.
So, any point to pick? And if you also want, you can think of throwing a parabola onto this as well. I'm not sure how to draw that accurately here, but yeah, so the point on the circle, semicircle, squared, plus the point on the parabola, squared. The y-coordinates are going to equal 1. Good. Just on this little segment right there. So, again, in general, these two graphs are the same on this neighborhood. Same graphs have same slopes. So I can simply take the derivative of both sides. So d dx, like we showed, plus 2x plus 2y times dy over dx, and the right side was 0. And we can do this for any nice shape, like the little folium we had earlier. Your little petal, oh, that was crap. Okay. Let's try it again.
Does the folium graph like hit the y-axis and the x-axis?
Yeah, it hits the origin.
Origin, okay.
So, pedal down. Oh, kind of looks like an octopus, doesn't it?
Okay.
Instead of missing 6 legs. So yeah, even with this guy, I mean, we can't nicely find a function like this. In fact, square root of 1 minus x squared doesn't just match here. It matches everywhere, right?
Right.
Right? That's not necessarily true. In fact, it's usually not true in the cases of graphs like this. X cubed plus y cubed minus 6xy equals 0. But still, I can do the same thing. You pick a point, again, it's on a case-by-case, point-by-point basis. Pick any point on here and realize that because of the smoothness, we can find some neighborhood for which there exists some function, let's say y of x, that exactly matches the graph on that interval, on that neighborhood, sorry. And so then you do what we did here. We can say that a equals that on the interval, and then we just derive both sides. So again, your starting point for this thought process is really point specific. You start by picking a point. And that might not be obvious based on how we did the computations. In the computations, the point was kind of the last thing we thought about, right? Yeah. We just threw that at the end. The theory behind it is really based on starting with a point. Starting with a point on a nice graph, and doing this process here.
We tend to say neighborhood and interval. You can also say interval, right, instead of neighborhood.
No. Neighborhoods are, they refer to a region in like a 2-dimensional space, 3-dimensional space even. Intervals are usually referring to 1-dimensional space.
Okay.
Like on the x-axis, on the y-axis.
Okay.
So usually they're not interchangeable in math. All right, with that in place, I want you guys to find. So now that we know the y behind the computation, let's go back to the computation. Find the slope at the point 3, 3 on the folium of Descartes. So take a minute or two to try this. All right, so how'd y'all do?
Pretty good.
Pretty good? Pretty good? What is pretty good numerically here? What did y'all get for your final answer?
Got a -1.
-1? All right, so let's see how this goes. We take the derivative of the left side. And this equals the derivative of the right. And at a particular point we pick. So, doing this, I can distribute my differential operator to every term in this bracket, like so. At the point I can pull out the 6 from my derivative, because again, this is just a constant. I'm allowed to do that. And so I get this. 0 on the right, and this on the left. So, Victoria, help me out here. What is this first derivative?
3x squared.
Right. The variables match, so it's a simple 3x squared. Alright, in this one though, the variables don't match, so I need to do what rule?
The chain rule.
Chain rule. This guy is the derivative of y cubed with respect to y times the derivative of y with respect to x. Alright,
That's 3y squared.
that is 3y squared. But again, don't forget the dy over dx because that is part of your chain rule. Now, for this term here, what rule do I have to implement?
The product
How should I
rule.
tackle it? Yes, product rule. So, this guy is x times the derivative of y plus y times the derivative of
X.
x. Of course, the derivative of x with respect to x is just
1.
1. Variables match and simple power. Just 1. So, throwing all this together now in one line, let's go up here. I have 3x squared, 3y squared, dy dx, minus, I got that 6 hanging out front, so I can distribute it now. Minus 6 times x dy dx. And then plus times a minus, and again, still minus 6.
6y.
6y, yes. That equals 0. Now, again, the goal is to solve for dy over dx. So how can I do that now, with this in place?
So we should bring all numbers with dy dx on one side and all numbers without it on the other.
Absolutely. It's just an algebra problem now. Bring your dy dx terms to one side, and everything else you pop it on over to the other. So, how can I do that?
You can add 6x to both sides and subtract 3y to both sides.
I could, but I'm more to write in that case then. I gotta write dy over dx in this.
Okay, so you can subtract 3x squared from both sides and add 6y to both sides.
Yes. So, I get 3y squared dy over dx minus 6x dy over dx equals negative 3 x squared plus 6y, yes?
Yeah.
Now, I got some numbers in front of every term I noticed. Do those numbers have anything in common?
3. Yes,
3.
3.
So if I want, I can just divide everything by its common factor. Greatest common factor of 3. So I get something that's even nicer to work with here. So I get y squared times dy dx minus,
2x.
yes, 2x dy dx equals negative x squared plus what?
2y.
Plus 2y, good. And now what was the point of getting dy dx to one side?
So that you can factor it out.
Yes, you factor it out, and after you factor it out, what do?
You can divide on that distributive factor to the other side.
Yes. You divide what's left over to both sides. So dy dx is this nice number here. Negative x squared plus 2y all over y squared minus 2x. And so final step is just saying, okay, this is the value of it at any arbitrary point xy we pick. But if we pick the point 3, 3, so at 3, 3, this guy equals what? So help me out in writing this expression.
So we'd put 3 in for x and 3 in for y.
Yes.
So that would be negative 3 squared plus 2 times 3 all over 3 squared minus 2 times 3.
Yes.
It's the same.
And that equals 9 plus 6.
So negative 9
Negative 9
plus 6,
6.
all divided by
9 minus 6.
9 minus
And
6.
That's equal.
It's a very nice negative 3 over 3.
Yes.
Which comes out to be negative 1. Does that gel well with the picture here? So here was 3, 3 was my point there, almost on the peak. Almost. But if I take a slope of that point, is it going to be negative visually?
Yes.
Yes. So at the very least, our numerical computation gels well with our visual intuition.
Yeah.
So that's one way you can kind of partially check your answers to these, if you have a picture. So, pretty cool, right?
Mm-hmm.
We have graduated from taking the slopes of functions at any points x and y to find the slopes of nice graphs that aren't functions. Circles, foliums, there's an infinite array of these things. And you guys will see much more of this in your practice problems. Jordan, you have a question?
I'm just curious. I mean, I know we got the problem right, and I'm just curious how the negative 3 squared turned into negative 9.
Right.
Weirdly.
So here, it's not going to turn into positive 9 because I don't have parentheses around this.
Okay.
Without parentheses, it's implied that you square the thing first. So this really means this.
Okay.
Okay? So the parentheses are a big deal. They make a difference, always. So yeah, again, a cool problem where you can find the slopes of graphs that aren't functions. And that just expands our repertoire to an infinite degree. We can do functions, we can do circles, we can do foliums, we can do a lot of weird things. And that's how you do it computationally. But I want to emphasize, again, the theory is that we don't consider the point at the very end. In the theory, we start out with the point. We pick any point on this nice graph, we zoom in, and because we realize that because it's a nice graph, then there has to exist some function, y of x, or f of x, however you want to think about it, that exactly matches the graph of the original in the neighborhood of that point. Again, because the graph of the original is a very nice graph. Does that make sense?
Yeah.
And with that in place, then, if they're exactly the same graphs, I mean, not only is y the function of x, where you can think of it as some function of x and take the derivative, but the slopes are equal in that neighborhood. So then you can take the derivative of both sides, and it's a true statement. But it's all starting out on a point-by-point, case-by-case basis. The theory, anyway. But the computation, it just kind of goes in reverse. So, any questions about this? All right. So the big computational theme of the day was using what rule?
The chain rule.
Yes, the chain rule. I mean, sometimes we saw some product rules popping in, some quotient rules popping in there. It was really all about the chain rule. Just a specific case where u equals y. And we saw just how essential, when you're starting out with this stuff, it was to use Leibnizian differential notation. But you guys are soon going to get to a point where you can start skipping the derivative operations, or writing them out anyway. So, if you have a nice simple relation like x squared minus y squared equals 16, when you get enough practice with these, you can just jump straight to the point where, okay, I take the derivative of both sides with respect to x. That first one becomes 2x.
2x. Yeah.
The second one becomes
2y times dy dx.
2y dy over dx. And that equals
0.
0. And then if you want, you can solve this for dy over dx. It comes out to be negative 2x over negative 2y, which is
X over y.
x over y. And the takeaway is, once you get comfortable with these, and at least for these relatively simple ones, you can skip writing the differential operator and doing distribution with it, doing quotient rule and product with it, and seeing that operator visually. You don't have to do that once you get pretty comfortable with these things. So likewise, this one, let's have x squared plus y cubed plus y squared plus 3 equals 0. Yeah, it's going to generate some nice shape in the coordinate plane. And I can write what derivative expression? Just right off the bat, without having to do operators. I can just say this is
2x plus 3y squared.
Yeah. This implies 2x plus 3y squared
dy dx.
dy dx
Plus 2y dy dx.
plus 2y dy dx plus 0, right? Equals 0. And once again, you can jump straight to solving for dy over dx. Let's skip some steps here. You can group these two together, bring this guy to this side, and then divide to get this equals negative 2x all over
3y squared plus 2y.
Yes. Alright, now how about this one? So again, let's try to do this without operator notation. 2 sine of x times cosine of y equals 1. So if I take the derivative of both sides, what do I get?
Well, we have to use the product rule.
Yes.
So we first get 2 times cosine of x times cosine of y.
Yeah, if you want to take the derivative of sine of x first, we get 2 times cosine of x. Cosine of y.
Plus negative 2 sine of x sine of y times dy dx.
Yeah. All times dy over dx.
And that equals 0.
That equals 0, yes. And you can solve this guy for dy over dx. He's going to end up equaling. You can bring this over here. And so, you have cos x, cos y.
Over
All
sine
over.
x sine y.
Yes, exactly. Sine x, sine y. Does that make sense? Good?
Yeah.
All right. Now, I want you guys, well, actually, I'll show you guys this. So sometimes you have variables that are kind of weird with the chain rule. So let's say I have something like this. X squared times sine, let's say x plus y. Suppose we choose the set of points in the coordinate plane x and y where this always equals y. I ask you to find the first derivative. Find dy dx. So this one, I'm going to do this in differential operator form, just so you can see the reasoning behind it. So if I d dx both sides, of course I get dy over dx on the right. On the left, what rule do I have to do to start?
The product rule?
Yes. So it's going to be x squared times the derivative of sine of x plus y with respect to x plus the derivative of x squared, right? Times this guy. So and that equals dy over dx. So you, Victoria, what does that equal?
That's 2x.
That is 2x. The hard part of this computation comes in finding what though?
Sine of the derivative of sine of x plus y.
Yeah, how do we do this guy? So again, the variable inside the sign, for the sign input, doesn't match this, right? So that's your trigger to use what rule?
The chain.
Yeah, again, if these variables don't match,
Yeah.
use a chain rule.
Chain rule.
This guy I can write like so. The derivative of sine of x plus y with respect to, it's kind of nifty here. What do you want to put there?
X plus y.
Yeah, I want them to match, because if they match, then I have a very simple derivative, right? They match right there, and of course at the end here I got the derivative of x plus y with respect to x. So, help me out here, Victoria. What's that first piece equal?
Cos x plus y.
Yes, they match, so it's just a simple cosine of x plus y. Now for this one, I have to do some little distribution, but this is the derivative of x with respect to x, which is just
1.
1, plus the derivative of y with respect to x, which is
dy over dx.
dy over dx.
Huh.
So now look, I've totally gotten rid of all my derivatives except for my dy's over dx's. So now we're just in algebra land again. So let's throw all this together here. I got
And you'll have to distribute the cos x plus y into the 1 plus dy dx, right?
Yes.
Okay.
So let's see. I got x squared all times cosine of that stuff times 1 plus dy over dx plus 2x sine of x plus y. That equals dy over dx. We all good?
Yeah.
Okay, what should I do next?
Factor and distribute the cos x plus y.
Right.
1 plus dy dx.
I need to work with this first term. That's the messy term, as
Yeah.
of right now. All right. So I can just take this. If I want, I can put the x squared right in front of cosine. Yes.
Mhm.
And say this guy is x squared cosine of x plus y times 1, so it stays itself. Plus what?
X squared cosine x plus y all times dy dx.
Yes. Times dy over dx. And I got all this stuff hanging out right. 2x sine. That equals dy over dx. Alright, next to last step is to do what?
Bring the dy dx terms on one side and the non-dy dx terms on the other
we
side.
We're back in algebra land. So minus this term. To both sides. And kind of out of space, I'll just say, that's the same thing as this. So, let's see here. X squared cos 2x sine equals dy over dx minus all this, right?
Right.
If I want, I'm just going to say a little spacer, I can factor out the dy over dx on the right side. And I get 1 minus what?
X squared cos
X squared
x
cos.
plus y.
And yeah, the final step is to do what?
Divide both sides by that.
Yeah, divide both sides by what's left over after you factor. So dy dx equals this this unholy mess here. It's kind of pretty.
Divided by
It's kind of pretty. X squared cos plus 2x sine all over
1 minus
1 minus x squared cosine of x plus y.
fun.
That is fun, and don't forget what this represents visually. Whatever this graph, this original graph looks like, if you want to find the slope of that point, any point there, you just throw it in this this beautiful, beautiful thing, this happy thing.
Nice.
So again, you can also get to a point where you can do this pretty quick, maybe without the operator rule, but I would recommend when you do get to more complicated stuff, if you have time to check your answer, fall back on doing it piece by piece, bite-sized pieces, operator notation. Does that make sense?
Mhm.
All right, so everyone, thanks for sticking with me so far. This was a rather long lesson. But just to reward you for your patience, and for those of you seeing this online, here is a mathematical truth of immense profundity. What is the derivative of a cow?
Shut up.
You can't talk to your teachers that way. Alright? Can't talk to your teachers that way.
I don't know what.
You don't know?
No, I don't.
It is prime rib.
Nice.